Good evening to everybody. In this talk, I will present a new study about the epidemic risk assessment applied as a case study to the COVID-19 outbreak in Italy. This is an interdisciplinary study made in collaboration with many colleagues from University of Catania, Alessia Emanuele Biondo, Nadia Giuffrida, Giuseppe Inturri, Vito Latora, Rosario Lemoli, Andrea Rapisarda, Giovanni Russo, and Chiara Zappalà. It is well known that COVID outbreak now reached 65 million of cases around the world, with about 1.5 million deaths, but the spatial distribution of damages is far from homogeneous. This is true over different spatial scales. For example, looking to the epidemic diffusion in Europe, it is clear that different regions in different countries have been affected in a very different way by the virus. In this study, we will focus on the epidemic diffusion in Italy, where it is evident that impact is quite different going from northern regions towards southern ones. One could speak of 3 different Italies. As you can see, at the end of the first epidemic wave in July 2020, more than 80% of cases and deaths were concentrated in the 8 northern regions in red, while only less than 20% in the other 12 regions of center and south. Also, intensive care occupancy, close to the epidemic peak in April, was mostly concentrated in the north. The details of this data for the various Italian regions can be appreciated in these color maps for total cases, deaths, and the intensive care occupancy. Looking at the change in the percentage of deaths in 2020 with respect to the average of the previous 5 years during the first epidemic wave, one can notice again a noticeable increment only in the northern part of the country. This unequal distribution of COVID effects in Italy is even stranger, as several recent studies showed that the virus was already circulating since September 2019. Therefore, it had had enough time to spread over the whole Italian territory, well before the mobility restrictions that in Italy were applied only at the beginning of March 2020. So, why was there such a different impact of the disease in the various Italian regions? The approach proposed in our study, whose preprint is available on the scientific report repository, offers a possible explanation. Conventional risk assessment theory relies on the Crichton risk triangle. In this framework, risk is evaluated as a function of 3 components: hazard, exposure, and vulnerability. For the purpose of this study, we can consider hazard as the degree of spread of the virus among the population of an Italian region, which is affected by a set of risk factors related to spatial and socioeconomic characteristics of the region. Exposure is the amount of people who might potentially be infected by the virus as a consequence of the hazard. Thus, it should coincide with the size of the population of that region. Vulnerability, the third component of the risk, is the attitude of an infected person to become sick or die. In general, it is strongly related to the age and initial health conditions before the infection. Among the many possibilities, we selected the following variables as risk indicators: mobility index, housing concentration, healthcare density, air pollution, average winter temperature, and the percentage of over 60 individuals in the population. The motivation under the choice of these variables relies on either generic epidemics literature and on recently confirmed features of the COVID-19 outbreak. Values in the table are extracted region by region from historical data collected in previous years. Each indicator has been opportunely normalized between 0 and 1. Notice that the temperature scale has been also inverted. Preliminary check has been performed for estimating the correlation of each single risk indicator with the main impact parameters of the COVID-19 epidemic. These parameters are, on one end, the total cases and total deaths cumulated in each region up to July 14, at the end of the first epidemic wave. On the other end, the intensive care occupancy recorded on April 2, close to the epidemic peak. The spatial distributions of the 6 risk indicators multiplied by the population of each region are here reported as chromatic maps, and thus can be visually compared with the analogous maps of the 3 impact indicators. Some correlations seem quite good also at the first sight. More in detail, we found correlation coefficients ranging from 0.71 to 0.96, always higher than those observed as a function of the population, which can be considered the null model. However, the relative quadratic errors stay quite high, from 0.26 to 0.62. This suggests that some proper combination of these risk indicators could be able to capture in a better way the global risk associated with each region. Such a goal has been realized through a multiplicative model for the evaluation of the risk index based on Crichton triangle. After several tests, we found that the best choice is to consider hazard and vulnerability as a fine function of, respectively, mobility index, housing concentration, and healthcare density on one end, and air pollution, average winter temperature, and age of population on the other end. Exposure is represented by the population of each region. Following the scheme shown in the figure, by multiplying exposure and vulnerability for a given region, we first recover the so-called consequences, which expresses the number of people in a given region who became ill for pathologies related to the virus. Then, by multiplying hazard and consequences, we will obtain the global risk index R, capital R, for each region. In this respect, the risk index can be interpreted as the product of what is related to the causes of the virus diffusion in a given region and what is related to the effects on people. Finally, two versions of this model have been tested. An optimized one, where the weights of the risk indicators are obtained through a least square fitting versus real COVID data, and an a priori one, where all the weights are assumed to be equal. At the end of the story, we definitely adopt the a priori version, since it results to be more robust. This is the reason why we call R the a priori risk index. Looking at the ranking of the Italian regions, compared with the COVID-19 data about total cases, deaths, and intensive care occupancy, updated both at April 2 and July 14. Notice again that data for cases and deaths are cumulated, while those for intensive care are daily scores. The values of the risk index have been normalized to their maximum value, so that Lombardia has R equal 1. Due to the intrinsic limitations of the official COVID-19 data, due to the fact that asymptomatic infected individuals are difficult to detect, it is convenient to make the comparison at the aggregate level of groups of regions without expecting to predict the exact rank within each group. Therefore, we arranged the 20 regions in 4 risk groups, each one characterized by a different color and ordered according to the values of the risk index. With this choice, our model is clearly able to correctly identify the 4 northern regions where the epidemic effects in terms of cases, deaths, and intensive care occupancy have been far more evident. The first in the ranking, that is Lombardia, with a risk score about 3 times more than the second classified, and the group of the 3 regions immediately after it, Veneto, Piemonte, and Emilia-Romagna, even if not in the exact order of damage. A quite good agreement can be observed also for the other 2 groups, where only a few cases were overestimated or underestimated. Notice that the proposed risk classification seems quite robust, since it holds both near the peak of April and at the end of the first wave in July, when the intensive care occupancy of the majority of the regions was 0. The clear separation between northern regions from central and southern ones is also confirmed in this slide, where the a priori risk color map is compared with the map of COVID-19 total cases in July on the left, and with the map of the serious cases and deaths of the seasonal flu in Italy on the right. The agreement is clearly visible already at the first sight, showing that our a priori model can be useful also for addressing other kinds of influences. In these plots on the left, we show the correlations between the a priori risk index and the 3 main impact indicators related to the outbreak. For each plot, a linear regression has been performed with Pearson's correlation coefficients that always takes values greater or equal to 0.97, indicating a strong positive correlation. On the right of each plot, we report a corresponding percentage of damage observed in the 3 Italian macro-regions, north, center, and south. Also in this case, compared with the percentage of cumulated a priori risk associated to the some macro-regions, the correlation is evident. Here we show 3 sequences of the geographical distribution of the total cases, total number of deaths, and current intensive care occupancy as the function of time, from March 9 to July 14. These sequences can be compared with the geographic map of the a priori risk level. In all the plots, damages seem to spread over the regions with a variable intensity, quite correctly predicted by our a priori risk analysis. Another interesting way to visualize our results can be obtained by representing the a priori risk index through its 2 main aggregated components, hazard and consequences, and plotting each region as a point of coordinates H and C in what we call a risk diagram. The value of the risk index is reported in parentheses next to each region name. This red curve is the ISO risk line corresponding to the average regional risk, R equal 0.15, which is able to correctly separate the 4 more damaged regions and highly risky that are in the north, plus Lazio, from all the other regions. Such a representation in terms of risk diagram may be used to build a policy model aimed at mitigate the damage in case of an epidemic outbreak like the COVID-19 one. In the final part of our study, we discussed some policy intervention proposals based on the a priori risk approach. We have seen that the risk index can be divided in 2 components. Thus, if we interpret the consequences in terms of protection and required support to people with the goal of improving the social results and reducing the economic cost, it is evident that enhancing the capability of the healthcare system appears to be the most important action, since it is insufficient carrying capacity that creates the emergency. To address this issue, we propose a theoretical model based on 2 independent variables influencing the level of risk in a certain region: the infection ratio, here the proportion of infected individuals over the total population, and the number of per capita hospital beds, as a measure of the impact of consequences caused by the spreading of the disease. We also provide some numeric example illustrating the subsequent steps that the policy maker facing an emergency outbreak should follow for the practical implementation of our model in a given region in order to minimize the risk level. In conclusion, our work is a first attempt to jointly consider different factors contributing to evaluate the a priori epidemic risk in a geographical area. Better medical knowledge and data availability will be important to further refine and improve the proposed methodology, which could also be easily applied to other countries, provided that they make the necessary information accessible. Further studies will deal also with dynamic implications, thus providing more specific intuitions according to different evolutionary paths of contagion spreading. Thank you for your attention.